Good morning and welcome to this lecture number 9 of the course Stochastic Hydrology. If you recall, in the last lecture we started with parameter estimation, especially we covered the method of maximum likelihood. The method of moments was covered in the earlier lecture. In the method of maximum likelihood, if you recall, we construct a likelihood function given a sample x 1, x 2, etcetera x n, and then we look for those sets of that set of parameters theta 1, theta 2, etcetera theta m, which will maximize the likelihood function. And in many situations, it will be advantageous to take the log of the likelihood function and maximize the log of likelihood function. Then we went on to introduce the correlation coefficient. Recall that correlation coefficient it provides a measure of linear dependence between the variables for which it is calculated. For example, we may calculate the correlation coefficient between rainfall and runoff. So, it provides the degree of linear dependence between rainfall and runoff in that particular case. Then we use this concept of correlation coefficient and developed a simple linear regression relationship between the variable y, which is a dependent variable, and the variable x, which is the independent variable. In hydrology, many situations arise where we will be looking for relationships between, let us say, rainfall in the catchment area and runoff at the outlet of the catchment. Essentially, what we did there is that in developing the linear regression relationship, we minimize the error between the observed values and the predicted values. Actually, we minimize the sum of squared errors. So, we are fitting a relationship y is equal to a x plus b, for example, and x are all the observed values and y is the predicted value using this relationship. So, you will estimate the parameters a and b such that the squared error, the sum of the squared errors is minimized. Today's class, we will introduce the important topic of data generation. Essentially, in most hydrologic decision making situations, we will have observed data for certain time period. Let us say you have observed data for the last 30 years on the stream flow. Using this observed data, you need to make decisions for the future. Many times, a situation will arise where the observed data itself is of short length and you would like to extend the data. Also, even if the data is of adequate length, because you are likely to make the decisions for the future, you would like to examine how this particular sequence of data that you have is likely to behave in future. So, the sequence itself will not repeat exactly, and therefore, you would like to look at several sequences which are likely to occur in future, and you will base your decisions upon these several sequences rather than basing on a single sequence. Then there may be also situations where you would like to fill the data. Let us say you have a continuous record of about 30-40 years, but in between there is certain length for which data is not available. Then you would like to fill this particular data. So, all these practical situations we address with data generation techniques and also data forecasting, which we will introduce subsequently, perhaps in today's lecture or in the subsequent lectures. So, we will see the motivation for the data generation techniques. Why it is necessary? Like I said, you have let us say a length of historical record. Let us say this is about 30 years, and you would like to use this 30 years of data at a particular location for, let us say you want to develop a reservoir project there. That means, you want to build a dam and then construct a reservoir there. The economic life of the project itself may be of the order of 100 years or 150 years. So, you are going to make a decision for the next about 100 years based on the last 30 years of data. So, you need to generate data for this economic life of the project. So, that you will study the implications of this particular project. Let us say you want to look at the size of the reservoir, that is possible, or you want to look at for a given particular size of the reservoir how reliably you can meet the water supply for a given set of demands and so on. So, they are all dependent on the flow that you have, flow record that you have, and therefore, using this flow record you would like to extend the data, the flow record itself for the economic life of the project, which typically may be of the order of 100 years and so on. Another reason why we do data generation is that if you use only this historical record, let us say you had 30 years of data and you make all the decisions based on just on this one sequence of 30 years of data, it will not give you an idea of the actual risks that are involved, especially when you are looking at the risks due to flooding or the risks due to droughts, hydrologic droughts, and risks due to inability of the system to generate the necessary power and so on. The third motivation for data generation is that the exact pattern of the stream flows or the exact pattern of the record that you have is not likely to repeat in future. Typically, we talk about the stream flows when you are doing the data generation. So, if you have a 30 years of record, this exact pattern is not likely to repeat. However, the information content that we have in this record, that information content if we use in some sense to generate several sequences of flows in the future, then that flow, that number of sequences will be useful for making better decisions and making better assessments of risk and so on. So, these are some of the motivations for which we develop the data generation techniques. The first level of data generation that we will introduce in this course now is if you have let us say the probability distribution of the particular variable. Let us say you are talking about stream flows, and from the last 30 years of observed data you have an estimate of the parameters, let us say means, standard deviation, etcetera, that we have learnt earlier in this course. And you also suspect that this particular record perhaps follows a particular given distribution, let us say normal distribution or exponential distribution and so on. So, if you are given a specific distribution with all its parameters estimated from the sample values, the question now is how do we generate sequence of values all belonging to that particular distribution. So, the problem is that you have the sample values, observed values of data, and you have fit a particular distribution to the observed values of data. When I say you fit a distribution, we mean you calculate all the parameters of that distribution, and then now we want to generate several such values which will all follow the same distribution. So, the idea here is that if the stream flow at a particular location, let us say follows normal distribution with mean mu and standard deviation sigma, can we generate several such values all belonging to the probability distribution, all belonging to the normal probability distribution with mean mu and standard deviation sigma? That is the question. So, the main principle behind the data generation that as we use in hydrology is that there is a statistical regularity of the hydrologic processes. Unless there are major changes that occur, for example, you look at the flows in a particular catchment, there is a statistical regularity of flows. If you look at last about 50 to 100 years, you may see certain statistical regularity of flows. Unless drastic changes occur in the catchment or the basin, this regularity is unlikely to be perturbed. For example, you look at this figure, the process was operating at a certain level, and unless there are certain physical changes occur, this shift as you are seeing here is very unlikely, whereas this kind of regularity is more likely in nature. Now, what are these drastic changes that we are talking about? For example, in a particular catchment, you do a large scale deforestation, or there may be a large scale fire that takes place, or as it happened recently, a tsunami occurs and then a large scale disturbance occurs in a very short time in the catchment, and therefore, all the hydrologic processes get perturbed or disturbed in a very short time. Unless such things happen, this kind of situations where the process was operating at a particular level and suddenly it shifts to another particular level, this occurrence is very unlikely. So, the principle that we use in data generation is that history provides a valuable clue to the future. Whatever has happened during the historical time period, we use that information to make an assessment of how this process is likely to behave in the future, and we use that principle to generate the data of the future. So, essentially we capture the essential information content in terms of the probability distributions, in terms of the statistical parameters, and in terms of the general stochastic behavior of this particular process, as we have seen over the history, use that information to generate values for the future. So, this is a general principle. Let us see how we do this. We also use the fact that there is a persistence in nature, especially as far as hydrologic processes are concerned. What do we mean by persistence? That maybe there is a tendency of flows to follow the trend of immediate past, that is low flows follow low flows and high flows follow high flows. So, the generating models reproduce the statistical distributions and persistence of historical flows when we are talking about generating models for the flows. So, in doing so, as I just mentioned, we have the historical data for which you would have calculated the parameters such as mean, standard deviation, correlation coefficient, and several other moments and statistical parameters. So, we develop models for data generation, which when used will reproduce the data, which will have the same mean as the historical mean or more or less the same mean. It will have nearly the same standard deviation as the historical standard deviation. It will have the same correlation coefficient as the historical correlation coefficient, and correlation coefficient we may talk about correlation between runoff and some other variables like rainfall, humidity, soil moisture and so on, or runoff at a particular time period with runoff at previous time periods. So, we are capturing the dependence on previous flows or other hydrologic variables such as rainfall, soil moisture and so on through correlation coefficient. So, when we develop the generating models, we will develop such that certain parameters or certain moments of the historical data are preserved in the sequence that we generate. So, how do we do this? As I mentioned, first we will look at the case where we know the probability distribution of the historical data and we want to generate several values all belonging to a given distribution. So, we are saying given a distribution, we want to generate data belonging to that particular distribution. This is the first simplest problem that we consider. The motivation for this procedure is that if you have the CDF, let us say CDF is from here, and any CDF you pick up randomly these values on the CDF. As you know, the CDF can vary between 0 and 1, the maximum value is 0 and 1. So, if you pick up randomly the values on CDF, they follow a uniform distribution in the interval 0 and 1. In fact, this becomes a very handy result which we use in data generation. Remember, this is irrespective of the distribution. So, as long as you have a CDF, the CDF values themselves follow a uniform distribution in the region 0 and 1. So, we use this result to generate values. Let us say we pick up a particular FU, the f of y, which is the CDF value at a particular y, and if you know the CDF relationship, analytical relationship, for example, in the exponential case, you know f of y is equal to 1 minus e to the power minus lambda y, where lambda is the parameter. So, if you know the analytical expression for f of y, you solve for y using the expression for f of y, and you put a random value for f of y. What is this random value? As I just mentioned, the f of y randomly picked up f of y's follow a uniform distribution between 0 and 1. So, you generate random numbers which belong to this uniform distribution between in the interval 0 and 1, set that equal to f of y and solve for y knowing the analytical expression for y, and that is the value of generated value of y, that is the generated value of y. Next time you change the f of y by changing the random number and generate another value of y, and so on and so forth. So, essentially what we are doing is f of y is given here. So, you may have an analytical expression for f of y. You set f of y is equal to R u, which is a uniformly distributed random number in the interval 0 and 1. From this R u, let us say R u is 0.234 or some such thing. So, you are saying f of y is equal to 0.234, and then there is an analytical expression for this. So, solve for y, and then from the analytical expression you solve for y, and that becomes the generated value of y. Next time you change the random number, you get another value of y, and so on. Now, how do we generate this uniformly distributed random number? Most of the scientific programs that you use on computer, for example, spreadsheets and Excel and so on, they all have built-in functions for generating uniformly distributed random numbers. That is, these RUs are obtained readily by uniformly distributed random numbers. Most scientific calculators also have a function for the random numbers. For example, I will show you here, I have a calculator, and it will have a random number generator. So, there is a random function here, I press, I get a number of 0.563. Then next time I press, I get a number of 0.966. Next time I press, I get a number of 0.229, and so on. Now, these are sets of random numbers which follow a uniform distribution with intervals 0 and 1, between the intervals 0 and 1. Remember, they are really random numbers. In fact, they are pseudo random numbers. I will tell you what are the pseudo random numbers presently. If I put off the system, if I put off the calculator and then again restart and again I generate, I will get a different number now, 0.318, and next one is again 0.323. And so, if let us say 10 of you try this experiment, all the 10 of you will get a different sequence of numbers, and that is why in fact they are random numbers. So, you generate random numbers, uniformly distributed random numbers, either by using a calculator like this, or if you are using a computer, most of the computer programs, most of the standard scientific computer programs like let us say you are using MATLAB or Excel, MS Excel and so on. These will have inbuilt functions for providing you uniformly distributed random numbers RU. So, you use them and then solve for your y, and you will use those many random variables as you need, as the number of values that you need to generate. Let us look at one simple example. Okay, another small point on the random numbers here. We call them as pseudo random numbers. Why do we call them as pseudo random numbers? Because there is an inbuilt algorithm that generates these random numbers. For example, when I say that I am using a calculator and then generating a random number, let us say I got 0.884 and I generate next random number 0.344. So, there is a inbuilt mathematical algorithm that is generating these numbers, and therefore, they are not really random, is it not? Because for the numbers to be truly random, the process that is generating has to be absolutely random. For example, you look at a radioactive material and then you are measuring the number of particles that it is emanating per unit time, let us say per 10 minutes or some such thing, per unit time the number of particles that it is emanating. Now, this is a truly random process, whereas the numbers that we generate through any of the computer programs or any or in the calculator etcetera are not truly random in that sense, because we are using a particular algorithm, and therefore, if you really generate really large number of values, after some time the sequence is likely to repeat, sequence will repeat, and therefore, the set of random numbers that we are generating thus are called as a pseudo random numbers. So, we have mechanisms or we have algorithms to generate the pseudo random numbers. While it is not really necessary, because as I mentioned, most calculators have this, most of the computer programs have functions to generate pseudo random numbers. We must at least know how it is generated. So, let us see a very simple algorithm by which a sequence of random numbers can be generated, which follow a uniform distribution in the interval 0 and 1. So, this is a simple algorithm for random number generator. Now, when I say random number here, RU indicates a random number which belongs to uniform distribution in the interval 0 and 1, that is what we denote it as RU. So, you look at this algorithm, xi is equal to a plus b xi minus 1 modulo m. Now, modulo m we define m modulo n, if it is there, we take the remainder of m divided by n. For example, 5 modulo 2, we divide 5 by 2 integer division. So, the remainder is 1, because 2 into 2 is 4. So, your remainder is 1. So, 5 modulo 2 will be equal to 1. So, we take the remainder of the integer division m by n. So, xi is equal to a plus b xi minus 1 modulo m, very simple algorithm. The m is essentially a very large integer value, a very large number, and a and b are fixed. So, in this algorithm you fix a, b and m, start with a particular number, given number x 0, generate x 1, use x 1 to generate x 2 and so on. So, like this you can generate. So, you get a sequence of xi. Xi by m are the required random numbers. So, you generate xi's and then xi by m, the sequence that gives the sequence of random numbers belonging to uniform distribution in the interval 0 and 1. We will take m is equal to 10. Remember, I told m has to be very large. Just for a demonstration, I am taking m is equal to 10 here. Typically, m is of the order of 2 to the power 32 or the maximum integer value that a computer can hold. Long ago, it used to be 2 to the power 32, but now it can be much higher. So, m is equal to 10, a is equal to 5, b is equal to 3. So, these are the constants that you use in this algorithm. So, let us say we start with x 0 is equal to 2, then xi is equal to a plus b xi modulo 10, that is 11 modulo 10. So, you divide 11 by 10, the result is 1. Now, we use this 1 to generate the next xi. So, this will be x 2 is equal to 8 and similarly x 3 is equal to 9 and so on. So, like this you get values of, you started with 2, then 1, then 8, then 9, 2 etcetera. So, the random numbers will be 2 by 10, 1 by 10, 8 by 10, 9 by 10, 2 by 10 and so on. Once this number repeats here, this is 2 by 10. So, this repeats here, because you are using the same constant values earlier as mentioned earlier. your sequence repeats. So, this sequence repeats. The length of the sequence before it actually repeats depends on essentially on this number m, but also to some extent on these parameters. So, the higher the larger the value of m, the larger is the sequence that you will be able to generate. So, this is one of the ways by which you can generate random numbers, uniformly distributed random numbers, and they are, remember, they are really pseudo random numbers. Okay, now that we know how to generate random numbers, that is uniformly distributed random numbers, let us see how we generate the data belonging to a given distribution. So, f of y will take lambda e to the power minus lambda y. This is the exponential distribution, lambda is greater than 0 and x is also y is also greater than 0 in this case. So, recall that the CDF is given by CDF is given by f of y is equal to 1 minus e to the power minus lambda y. So, as I said, equate this to, you set a random number from uniform distribution and then put that random number is equal to f of y. That means, you are randomly picking up f of y, that is the idea there. So, for r u dash is equal to 1 minus e to the power minus lambda y, and therefore, e to the power minus lambda y is equal to 1 minus r u. Because r u dash is between 0 and 1 and it is random, I can put this as r u, another random number. 1 minus r u dash itself is a random number. So, r u is equal to e to the power minus lambda y. Then we take logarithms. So, log r u will be equal to minus lambda y. Therefore, y is equal to minus ln r u by lambda. So, you generate random numbers r u, use the calculator for example. Every time you generate one r u, you get that particular value of lambda for a given that particular value of y, generated value y for a given distribution. That means, lambda is fixed there. So, once you fix lambda, generate your r u using a calculator and generate those many values of y. Let us look at a simple example now. So, generate 10 values from exponential distribution with lambda is equal to 5. First, you generate one random number, uniformly distributed random number. Let us say again we will take calculator and then get this number. And if that number is 0.026, lambda is given. So, you will get y. So, you get a y. Next time you generate another random number, as I mentioned, every time you take a new random number and then generate the associated value of y. So, like this you generate 10 values of y. The data generation has to be essentially done for a large sequence. You cannot just generate 5 values, 10 values etcetera, and then say that this follows the same distribution as the given distribution. So, if you generate not 10 values, but 1000 values, 10,000 values, 20,000 values etcetera, and then examine whether the sequence that you have so generated in fact follows the exponential distribution with lambda with the associated lambda, then it has some relevance. Let us see what happens. Let us say we have generated 5 values here, 10 values, I am sorry. You have generated 10 values. For these 10 values, if you get lambda, it comes to about 4.43. It comes to 4.43, and we had started with lambda is equal to 5. So, ideally I would like to have lambda is equal to 5, and I should be able to test that the sequence that we have generated in fact follows an exponential distribution. So, if you generate more values, let us say from 10 you went up to 100, maybe it improves further, lambda improves further. From 100 you went to 1000, lambda improves further, 1000 to 10,000 etcetera. So, ideally you generate a large sequence of values and then examine for the parameter. That parameter value must be as close to the parameter value for which you are generating the random numbers, random data as possible. And then you should also have ways of examining whether this follows exponential distribution, because of the basis by which we have constructed these data in fact follow the exponential distribution. Now, this was the example that I just discussed. It was conveniently possible for us to solve for y. What did we do? We solved for y knowing the expression for CDF f of y. So, this particular form is in such a convenient form that I could very easily readily solve for y. That is, we are looking for the inverse solution for y given f of y. But there are many situations, many distributions for which this is not possible. For example, you take the normal distribution. The CDF of normal distribution, if you look at, it is not possible for you to solve analytically for y given f of y, that is a capital F of y, which is a CDF of y. Similarly, gamma distribution, it is not possible for you to solve for y given f of y. In such situations, we may use different techniques or different ways of handling this difficulty. For example, in the case of normal distribution, what we do is we use the standard normal distribution. Y is equal to let us say you transform, that is z is equal to y minus y bar by sigma, that is how you transform and then solve for y. So, for various values of z you should be able to get y. How do we generate these various values of y z? That is, you want those random numbers which follow a standard normal curve, all right, with 0 mean and unit variance. Now, these are tabulated and available. They are called as standard normal deviates. So, we denote them as Rn. So, Ru we indicated as uniformly distributed random numbers in the interval 0 and 1, and Rn are standard normal deviates which follow a normal distribution with 0 mean and unit variance. Now, these are available, these tables are available, and also many of the programs, scientific programs, have functions that you can call them in your programs to generate directly Rn. Once you have these Rn values, that is the random numbers, you can generate the data y is equal to sigma Rn plus mu. How do we get this? This is y minus mu by sigma, which is the standard normal deviate z. So, you given Rn, you should be able to get y for a given normal distribution with parameters mu and sigma. So, let us have a look at one simple example here. So, we want to generate 10 values from a normal distribution which has mean as 10 and variance as 15 square. So, we write y is equal to sigma Rn plus mu. So, mu is given and sigma is given. So, we generate Rn with from standard tables or some such thing. So, here we use the Rn values. These are taken from a standard textbook C.T. Hahn, which I have given reference in the first lecture. So, we take these random numbers from a table which is provided in this particular textbook. Every time we change the Rn and get one particular value of y. So, y is equal to sigma Rn plus mu, you get this y. Next time you change the Rn, you get another value of y. Change the Rn, you get another value of y, and so on. Like this you get. So, again you check whether what is the mu that you are getting, what is the average value that you are getting out of the generated numbers. So, this comes out to be 14.86 and the standard deviation comes out to be 191.65 as against 13.8 standard deviation as against the 15 that you started with, and this is quite close, this is 14.86 as against 10. Again, if you generate not 10 values, but 1000 values, 10,000 values, 20,000 values, etcetera, using this procedure, you will converge to a normal distribution, that is the generated values will approximate a normal distribution with a mean of 10 and variance of 15 square. Then there are certain distributions for which even obtaining these tables is difficult, analytical values of these tables are difficult. but they may be related to some other distributions for which data generation is possible using analytical procedures. For example, you look at the gamma distribution. In the gamma distribution, for the specific case where eta is integer, that is for integer values, it has been shown that gamma variate with integer values of eta is actually sum of eta exponential variates with parameter lambda. Gamma distribution has two parameters, eta and lambda, and the exponential distribution, which if you recall is a special case of gamma distribution, that has one parameter lambda. So, for integer values of eta, the gamma variates can be equated to sum of eta number of exponential variates for integer values. So, for example, y is equal to we then write y, which is a gamma variate. We want to generate a gamma variate is sum of minus log r u I is equal to 1 to eta by lambda. What is this log r u by eta minus log r u by eta? Just now we saw for exponential distribution, we just saw that the expression for that is minus log r u by lambda. So, we use this exponential distribution, sum it eta number of times. If eta is equal to 2, for example, you generate 2 random numbers, uniformly distributed random numbers, and then sum it the exponential variates and to obtain the gamma variate. That is the idea here. So, for eta is equal to 2, which is an integer number, you get y, which is a gamma variate in this case, as minus log r u 1 plus log r u 2. So, you need two random numbers, two uniformly distributed random numbers to get one gamma variate, one data belonging to the gamma distribution with eta is equal to 2. So, let us use that expression and then generate 10 values for that is 10 values belonging to gamma distribution with eta is equal to 2 and lambda is equal to 3. So, we are specifying the distribution and we want to generate those many values. Because eta is equal to 2, you need two random numbers to generate every number belonging to the gamma distribution. So, r u 1 and r u 2, you get two random numbers, again using a calculator or something, you get two random numbers, two uniformly distributed random numbers, and you generate y. So, y is equal to minus log r u 1 plus log r u 2 divided by lambda. Lambda is given, therefore, you generate y. Like this, you generate 10 values of y. You can generate again 1000, 10,000, 20,000 depending on the need. You can generate as many values as you want, and then you can finally check for the parameters. In this particular case, for these 10 values, you get a parameter eta cap estimated from the generated values comes to 1.95 and lambda cap comes to 2.41. All right. So, what we did in data generation is that we specified the distribution. When we specify the distribution, we specify also the parameters of the distribution. We say that normal distribution with a particular set of parameters mu and sigma square, and then generated values belonging to that particular distribution, the data that belongs to the particular distribution. Remember here, we did not build in a dependence of the data on the previous value. Say for example, this particular data does not depend on the data that is generated previously. Similarly, this data does not depend on the data that is generated previously. So, we are saying that it is a purely random process which follows a particular distribution, let us say Gaussian distribution or gamma distribution, etc. So, every time period, let us say you are talking about a sequence of flows here. Every time period you are picking up a randomly generated data belonging to that particular distribution. You are not worried about its dependence on the previous values that have been generated, and that is why we did not talk about the correlation of one value on the previous values. So, simply you are generating data based on a given distribution. So, all these are random numbers belonging to that particular distribution. Now, we come to an important topic in stochastic hydrology, and that is the time series analysis. Actually, this is the way we cover in this particular course is just an introduction to time series analysis. The time series analysis is a course by itself. Typically, we offer a 3-credit course on time series analysis, but as part of stochastic hydrology, we just introduce the concepts of time series analysis. Time series analysis plays a very important role in hydrologic data generation as well as hydrologic forecasting. In many cases, we will be interested in, let us say, standing at the beginning of June month, we may be interested in forecasting the flows for the season June, July, August, September. In monsoon season, if we are interested, we would be keen to have a forecast for the seasonal flows, for the seasonal rainfall and so on. So, that we can start planning of how to operate the reservoir, how to plan for the cropping patterns and so on. Time series analysis also comes in very handy. The techniques of time series analysis come in very handy when we are looking at data generation. That is, you want to generate data for, let us say, next 100 years, 500 years and so on, because we want to simulate the system using this synthetically generated data and to look at what are the risks that are involved in making a particular decision. In such situations, the time series analysis comes in very handy. What we did in data generation, same thing we now take it forward, except that in the time series analysis we are talking about a sequence that has been observed over a period of time, and therefore, there is a dependence of one value on another value that is observed, and this dependence we bring in now. So, what do we mean by time series? Time series is a sequence of values of a random variable collected over time. Let us say you are talking about stream flows. When we say stream flow time series, we have it is a observed values of stream flows across time. Let us say last 50 years, every month we have observed the values of stream flow, and this sequence of monthly flows observed over last 50 years. This constitutes a time series. Rainfall values observed every day, every 24 hours we are observing the rainfall values for the last 10 years. This constitutes a time series. So, we are making observations on a given random variable with time. That means, the realization on that random variable across time, that is called as a time series. Now, these observations may be made at discrete times. For example, rainfall, we may be measuring every day 8 o'clock in the morning. So, today I measure at 8 o'clock in the morning, and tomorrow I will measure again at 8 o'clock in the morning, and then we estimate or we provide the measurement for a daily rainfall, for the rainfall during that particular day. So, or monthly stream flows, you may be observing you may be observing every day, but you will average it over the month, you aggregate it over the month and provide monthly stream flow value. So, like this you may have observed data at discrete time intervals. So, your delta t or the time interval can be either 1 day, 1 week, 10 days, 1 month, 1 year, 1 season and so on. You may also have continuous time series where the recording is available on a continuous scale. For example, if you are doing an experiment and then you are measuring continuously, let us say pressure measurements or some such thing, you are measuring continuously. Such time series constitute the continuous time series. In most hydrologic situations, we will be dealing with only discrete time series. We will be talking about daily time series of daily rainfalls, time series consisting of monthly stream flows, daily evapotranspiration and so on. So, we will be dealing with essentially the discrete time series. More precisely, it is called discrete time series. That means, the time is on discrete scale. A single time series that you have observed is called as a realization. For example, we may have flows between 1900 to 1950. This is one time series. A single time series is a realization. You may have several such realizations. For example, you may have flows between 1950 to 1975, then 1900 to 1925, 1930 to 1950. Same random variable observed at different time, different windows of time, you get a different time series, and therefore, you get different realizations. The collection of all such realizations is called as an ensemble. So, an ensemble of time series consists of a collection of all realizations. For example, x t 1 is one time series or one realization, x t 2 is another realization, etcetera. Like this, you may have m such realizations, and the collection of all such realizations is called as an ensemble. This is shown graphically here. Let us say you are talking about stream flows, and then you may have one realization between 1920 and 1950. This is a realization. Then you may have a second realization between, let us say, 1970 and 1990. This is another realization. Like this, you may have m different realizations. So, these sets of m realizations constitute the ensemble of time series. In hydrology, generally we will have only one realization. Typically, hydrologic time series are notorious for the short length that they possess. Typically, if you have data for 50 years, it is supposed to be very useful. So, you may have maximum of typically you may have series or time series of about 50 years of flows. But when you want to have several realizations, you can split this time series into several shorter time series, shorter realizations. Let us say you have for the last 50 years, then you may split it for first 20 years, next 20 years, last 10 years and so on. Like this, you may have several realizations just to examine how the time series is behaving across time, whether the properties have remained stationary and so on. So, you can split the time series. But however, as I said, in hydrology we are handicapped with large lengths of data. So, you may have to deal with one or maximum of two realizations in most cases. Let us say you look at a particular time series, that is, you have observed stream flows, let us say for last about 50 years or something. If you simply plot this, that is time t versus x t, this may be stream flow. If you simply plot this, it appears something like this. This is called as the time series plot. So, the moment you have a data, first you plot a time series, the time series itself. So, this is called as a time series plot. This is simply the plot between x t and t. As you can see here, if you take the long term mean, which remains constant, the values are fluctuating around that long term mean randomly. So, there is a random fluctuation of the values observations around the long term mean. Not only long term mean, there may be several such deterministic numbers or deterministic parameters or the movements around which the values may be fluctuating. So, if you want to replace the time series by a mathematical model, you will write this simply as x t is equal to a deterministic component. At every time here, there is a deterministic component which is mean in this particular case, around which there is a random fluctuation. So, we write x t as d t at that particular time plus epsilon t. In this simple example that I have shown here, dt is equal to d is equal to mean, that is all across the time we are saying that the mean remains constant and around the mean the values are fluctuating randomly. So, x t you write it as a deterministic component plus a random component epsilon t. So, the challenge of the time series analysis is precisely to identify this dt and epsilon t. Once you identify what is the nature of dt and what is the mathematical nature of dt and what is the mathematical nature of epsilon t, you write x t as simply equal to dt plus epsilon t. So, there are certain random fluctuations of the process occurring around a deterministic component. Now, what are the typical deterministic components? One may be a situation where there is no deterministic component at all, the values are all randomly fluctuating. Take for example, these are different components of the time series. If you have only stochastic component, that means there is no deterministic component at all, there is a random variations, they are all purely random. So, this is purely stochastic, there is no deterministic component involved here. For example, very short duration rainfalls, if you take, let us say you are taking half an hour rainfall, 30-minute rainfall and so on, and plot it for a long period of time. Simply collect at a particular location half an hour rainfall and then plot it against time. That may be showing such feature that it does not have any deterministic component at all. But you may also have a trend in the data around which the values are fluctuating. If you look at, for example, the global average temperatures over the last few years, last 30 years or some such thing, there is a increasing trend of the temperature values. So, this indicates the trend line and then around which there is a random fluctuation. So, the deterministic component in this particular case is the trend. You may also have periodic processes. For example, you look at the monthly stream flows in a typical monsoon climates like ours, you just look at the monthly stream flows, you may have a periodicity associated with them. So, there is a periodicity, there is a periodic process and around which the values are fluctuating randomly. Then you may also have a jump as shown here, that is the process was operating at a particular time level and then suddenly it takes a jump and starts operating at a different time level. As I mentioned earlier, such kind of jumps or even the drops may occur because of sudden changes, sudden large scale changes in the catchment. Let us say there is a sudden large scale deforestation that takes place or sudden large scale fire that breaks out or an earthquake occurs of a high magnitude. All of these will perturb the hydrologic balance. So, what was operating at certain level suddenly starts operating at certain other level, or even let us say a large scale rapid urbanization of a catchment through which your groundwater usage suddenly increases on a very large massive scale, then the hydrology will respond in a short time, it responds with certain jumps like this. So, there is a jump here around which the values are fluctuating. Then as I mentioned, if you want to write x t is equal to d t plus epsilon t, the deterministic component may consist of one or all of them. It may have a trend, it may have a long term mean, it may have a periodicity, it may have a jump and so on. So, you must be able to identify the deterministic components which can be a combination of several of these, and then we should be able to identify the random components. So, there is a random fluctuation around the deterministic components. So, the in the discrete time scale, which we will be focusing on, we are dealing with observations at specific times separated by delta t. So, when we plot a discrete time series, we will be plotting at let us say monthly stream flows if we are plotting June of 1950, July of 1950, August of 1950 and so on. So, like this at every time you have one point and then there is a delta t, which is the time interval between two observations. Whereas, in the continuous scale the data will be continuous. For example, when you are doing the turbulence studies, pressure measurements etcetera in the laboratory, you will generate continuous data. So, in today's class now, to summarize, we started with data generation and provided the motivation for data generation. What are the major motivations? Major motivation is that you have only observed historical flows, historical data. Typically, flows is what we will be interested in most hydrologic decisions. You have only one sequence of data. So, you would like to examine the behavior of this process in the future. So, obviously, you cannot place your decisions or place your judgment only on one sequence. So, you may want to generate several sequences all belonging to the same distribution as the historical data. So, we introduce methods by which you can generate data belonging to a given distribution. For example, the exponential distribution, gamma distribution, normal distribution etcetera. What is the basis on which we develop this? The basis is that the CDF, if you pick up randomly the values from a given CDF, these values will follow a uniformly distributed uniform distribution in the interval 0 and 1. And therefore, we generate uniformly distributed random numbers, equate it to f of y, solve for y given the analytical expression for f of y and thereby get the value of y. Every time you change the random number, you get a different value of y, and that is how you generate a sequence of data belonging to that particular distribution. Then we went on to introduce the concept of time series. As just mentioned, the time series is a series of observations across time on the same random variable. For example, you may have a stream flow at a particular location and you have made the observations of stream flow every month for the last 50 years. So, this set of observations constitutes a monthly stream flow time series. The idea in time series is that you want to reproduce these observations with a mathematical model. It can consist of a deterministic component and a random component. So, the deterministic components themselves may consist of a long term mean, it may be a mean, it may be a trend, it may be a periodic process around which the random fluctuations are occurring, or it may be a jump or a drop. So, in the next class we will in the next lecture we will see how we take forward this simple expression that we got x t is equal to d t plus epsilon t, that is the time series consisting of a deterministic component and a random component. How we analyze the time series. This is what we discuss in the next course, next lecture. Thank you very much for your attention.